All right, let's get started. Welcome back. Hope you had a nice break and are refreshed. So one more session, that's it. So we have some short industry talks in this session, 5 talks. And I do want to say right after this, we will walk over to the faculty club where we will have a cocktail hour and then we have dinner. And please stay for dinner and there'll be good food and lively conversation. And hopefully all the rain will subside by then and you can drive back when it's dry. All right, so with that, let's get started. We have 5 talks, as I said. The first talk is by Gumaro Rendon on canonical partition function on a quantum computer.
Thank you. So I'll talk a little bit about the work we did last year with an intern. It's a collaboration with our intern Taoshi, Guo, Ratuja, Shirsagar, and me, Gumaro Rendon. But let me just give you a little bit of background about the problem. So partition function estimation in physics is a very important problem. It lets us estimate thermal observables, and that way we can characterize phase transitions in materials and whatnot. So basically, why use a quantum computer for this kind of problem? The classical cost in order to search the whole of the space, of the configuration space of the physical system, grows exponentially with the number of degrees of freedom. But when you use a quantum computer, the cost gets improved quadratically through what's called the quantum amplitude estimation algorithm. There's a question.
So, well, I just didn't understand if you go back
the notation.
To the slide, it's like 1 over 2 to the n. So
yeah, 2 to the n. N is the number of degrees of freedom, and what I call here capital N is basically the size of the whole Hilbert space.
Oh, it's just that whatever to the n gets smaller as n gets larger. So.
Oh yeah, I got them switched around. So that's basically the size. Yeah, that's a typo. Okay. So the cost is the inverse of that. Same goes for this one. So one other detail that you will have to take care of in this kind of problems is the encoding of the physical system. Typically, like the state-of-the-art methods require you to do what's called a block encoding. So you take a unitary encoding of a Hermitian matrix, where you select the Hamiltonian matrix with a ancillary register, and with that primitive, you then construct what's called we call a random walk operator, which transforms the eigenvalues and so it's a unitary now, but it transforms the eigenvalues with an arc sign. So we gotta take that into account when you transform the signal on the quantum computer. So the kind of transformation that we want to do on this problem is an exponential. We want that polynomial of the Hamiltonian. Yeah. It's a non-unitary, so we gotta use quantum signal processing methods to obtain this non-unitary operator. So these are the state of, a couple of years ago, these were the state-of-the-art methods. And there's been a series of works where we used more rudimentary Trotterization to approximate the Hamiltonian evolution. However, the kind of splittings to reduce the error on this Hamiltonian evolution, we need to increase the cost depth of the circuit, like 1 over epsilon, where epsilon is the target error of the operator, and we can do this a similar signal processing on this kind of using this kind of approximated evolution. Yeah, so that's, we define for the purposes of estimating the converging of our methods, or for estimating the errors of our methods, we come up with this effective Hamiltonian, which is as long as we stay within the branch of the principal branch, we can define this effective Hamiltonian that way, and it's an analytic function. So we use interpolation methods on these functions that depend on the size of the Trotter step. We make sure that these are analytic to ensure a good convergence rate. We've used it for interpolating the ground state. We use several samples for different Trotter step sizes, and we interpolate towards the zero Trotter step size using stable interpolation methods. There's been also work on doing this for the Hamiltonian evolution, the evolution operator. Now, let me talk a bit more about our work. We want to estimate the exponential operator using Trotter evolution operators and interpolation methods. That way, we don't have to use block encoding. Block encoding incurs into higher qubit requirements, and those we want to reduce that so that these methods can be implemented on earlier devices. So first of all, if our primitive is the Hamiltonian evolution operator, or the effective Hamiltonian evolution operator, and we want to transform this signal into another function, we use the Fourier series. We don't want this Fourier series to have any spurious Gibbs phenomenon, so we use what's called low-weight Fourier series, that as long as you stay away from the edges of the interval of interest, you have an exponentially convergent series. So it's very similar to what people did a few decades ago with modifiers, that kind of stuff. But here they use some intermediate Taylor expansions to obtain this result. Now, to estimate the partition function, we want to take the Gibbs factor, or the exponential, and take the trace of it to estimate the trace of the operator, right? But how do you do that? It's standard to use what's called thermophile double states, where you basically start with an even distributed superposition in computational basis, and then correlate that with basically you create a Bell pair, and you obtain that kind of state. And to obtain the trace of the operator you're interested, that is the Boltzmann factor here. What's the pointer? Sorry. Take this trace. You basically just project this unitary with respect to this state. This 0 here, this ancillary register, selects the Boltzmann unitary to give you this non-unitary operator. This garbage operator is orthogonal to the 0 state. So you basically get rid of that contribution when you project out. And this probability, this is a probability, well, this is an amplitude. The amplitude square is proportional to this over here.
Question?
Yes?
Is this related to Hutchinson's trace estimation?
Hutchinson's trace estimation. I'm not sure.
That's where you form V transpose AV, where V is a sort of random zero mean vector and average that, and that you get the trace.
Is that an estimation method or?
Yeah. In the non-quantum world.
Okay. Yeah, no, in this case, I don't know if they're related, but this here, if you go through the contracting of the vectors, because of this correlation here, when you contract with this on the other side, you select this element of the matrix here, and you basically obtain the trace exactly, except it's a quantum amplitude, so you have to repeat this multiple times to base the binomial distribution. Or if you use quantum amplitude estimation, you obtain a quadratic advantage or that naive sampling. Now, how do we get this exponential factor? More like, how do we obtain this unitary here? This whole thing. We take the signal. That basically, this is the unitary that gives you your basically your time signal, and you transduce it to obtain this. When you observe this, you start with a 0 on your qubit, and you measure a 0. Basically, you're implementing the non-unitary operator over here. It's much easier to see this kind of signal processing with the quantum Fourier transform. If you think of loading your time signal into a quantum register, which is basically memory storing your vector, which is a time signal, and you quantum transform that. Anyway, let me continue. Now the interpolation part is okay. Basically, to do away with the Trotter error from our approximation of the evolution operator, we use Chebyshev interpolation, which is the most stable kind of interpolation we can do. Basically, our function that we want to interpolate is this one that depends on S, the Trotter step size. And we solve this linear system. These are the Chebyshev polynomials, sample on the Chebyshev nodes. The eigenvalue of the van der Mondel-like matrix is all of the eigenvalues are 1, so the inverse is also unit. The norm is also unit, so it's very stable. Doesn't blow exponentially with the errors on your signal or your amplitude estimation. So this is basically the kind of scaling that we get. So we obtain what's the block encoding methods also get, which is this polylogarithmic, this logarithmic scaling with respect to the systematic error. This is the statistical error, and we also get this factor here, which improves the scaling for when using quantum amplitude estimation, and it's almost linear with beta, the inverse temperature. And this is the system we apply it to. It's a SIG model for studying superconductors, high temperature superconductors, and we save these many qubits. So it's sort of like a 20-30% saving in qubits. And other places where we use stable interpolation methods to improve quantum algorithms is this work. And I'll be happy if you have any questions afterwards. Thank you.
We can take a question. It's the next speaker session.
Oh, yeah. So you showed that graph with n Majorana. Can you talk a little bit about that?
You said that?
Yeah, that one. Yeah, yeah.
So basically, I didn't talk much about what the cost of block encoding entail, the methods that one uses for simulation of those. If you have this Hamiltonian with these many non-commuting terms, the number of qubits you need to block encode that grows logarithmically with the number of terms in your Hamiltonian. The sig model, the number of terms grows with a power of 4 with the number of Majorana fermions. So that's like a scenario where this could play a role, where you have a 20-30% improvement in the number of qubits for the system sizes you're interested in. So for early devices, this would be, could maybe let you implement this 2 years before than the other algorithms.
Thanks.
Thank you very much. Yeah. Yeah, next we have Anderson from Visa Research on deep learning with plausible deniability.
Thank you. Hello, my name is Anderson Nascimento. I'm with Visa Research, and I would like to talk to you today about privacy issues in machine learning. More specifically, I'll work on deep learning with plausible deniability. This is joint work with Wen Xuan and Vincent from the University of Florida, and Shan, Hadi, and Yue from Visa Research. But before I start talking about the result, I would like just to, I know there are students here, postdocs, and I just would like to tell that we are hiring. And even though my talk today is about privacy, we're actually starting a quantum computing group, quantum computation and information group at Visa, based here in the Bay Area. And we are hiring at multiple levels with multiple openings. We have an opening for a principal research scientist, staff research scientist. We also are looking for PhD interns. We have a broad range of interests, quantum algorithms, optimization, work with NISQ devices, but also, fault-tolerant research that requires fault-tolerant quantum computers, distributed quantum systems, and so forth. So if you're interested, please feel free to reach out to me. And if you know someone who is interested, also reach out to me. It will be a pleasure to explain those opportunities. Okay, after I have got rid of that. So privacy is a big deal in AI. Those deep learning models, they bring us all sorts of supposedly useful things for our lives, but they tend to have the nasty habit of memorizing stuff that has been used to train them. And this can be particularly troublesome if you're working with health data or, payments data. Of course, it's a big problem, and you'd like to do something about it. But thank God, we have some beautiful theoretical tools that help us deal with this problem, particularly differential privacy. So differential privacy is a rigorous definition of privacy that has all sorts of beautiful properties like immunity to post-processing, composability, and so forth. And by using differential privacy, actually, we can come up with techniques that allow us to train deep learning models in a way that prevents extracting individual entries of the data set that was used for training those models. And probably one of the most common ways of training a neural network with privacy, with differential privacy guarantees, is what we call DPSGD, or differentially private stochastic gradient descent. What I did here is really awful, right? You just write the algorithm, don't define the notation. It's a recipe to get people angry. But the main idea is, you have an input, you pass it through the network, you compute gradients, and then you have a threshold. And you see, is this gradient above a certain threshold? If it is, you just clip it. Otherwise, you keep the gradient as it is. And after that, you aggregate those gradients, and you add a noise. And the variance of this noise will be proportional to the clipping threshold. Okay, so in a sense, what you're doing is you are restricting the influence that each gradient will have in the final aggregated noisy gradients that will be in turn used to update the parameters of the network. So by removing or adding one specific entry, you somehow bound the influence that entry can have on the parameters of the network. And this is all very beautiful. You can get really strong privacy guarantees with that, but you do that at quite a high price. There are many applications where the utility that you get here is not good enough for the applications that you have in mind. Not just that, but also you have to compute those gradients individually. And that can be quite expensive from a computation and memory point of view. So what people do, well, they try to come up with heuristics. They come up with heuristic methods, empirical methods, that aim at reducing the likelihood that this model will memorize entries, or the likelihood that you can actually retrieve those particular entries by performing a membership inference attack. And there are all sorts of empirical methods, regularization, knowledge distillation, and so forth. But what we aim to do here is, well, we have those two extreme worlds. We have a world where you have very strong privacy guarantees, but then you pay a heavy price in terms of depending on the specific application, you may pay a heavy price in terms of utility, but also in computational and space complexity. And then you have this other world where you come up with heuristics that don't give you theoretical guarantees. They might work for some specific attacks, and they are more efficient to implement, and they give you better utility of the data. They give you models that have better accuracy. So can we do something in between? And that was the main motivation of this work here. So we come up with a different definition of privacy, which in the privacy community research is the equivalent of starting a holy war. So we all are very dear to the privacy definitions that we love, and usually very antagonistic to the new privacy definitions. But we try to come up with a definition that somehow sits in between those two worlds, that gives you some formal guarantees of privacy, while also giving you better utility models that actually have better accuracy and can be implemented more efficiently from a computational point of view. So this slide here shows standard stochastic gradient descent. You have a data set, you shuffle and you partition this data set into batches. You take one of those batches, you compute a gradient, and then you use this gradient to update the parameters of your model. And the main idea here is, maybe we could, rather than clipping those gradients to, limit their influence in the final model, we could take a look at gradient and say, well, is this gradient typical? In a sense that, depending on which batch you take, multiple batches would likely generate a gradient that somehow looks like that. And of course, you have to define what looks like that is. And that's basically the main idea that I'm going to explain more details, is to come up with a test here so that we can look at the gradient and say, is this gradient leaky? Or does it reveal too much information? In case it reveals, you just throw it away and you repeat the process, okay? And we call this notion plausible deniability, and I will explain to you why in a minute. I don't have a lot of time here. Yeah, so this is the main idea of our solution. You start with a batch of data samples, and then we pick up, let's say, a seed batch. You compute the gradient for that batch. Okay, and also what we do is we add noise. Okay, the idea of adding noise is that gradients will there will be a healthy probability that the gradients will overlap somehow after you add the noise. And then you perform a privacy test. I'm going to specify exactly what privacy test it is. If the gradient passed the privacy test, you update the models with it, update the weights of the model with it. It fails, you throw it away, and you repeat the process. Is that clear? So what privacy test is this? And the privacy test is, well, are there T, where T is a parameter, other batches in the training set that have similar gradients? And of course, you have to define what similar is. In the paper, we actually play with multiple definitions of similarity here, but this is one of the simplest ones. So if you have T batches in the data set that somehow produce gradients that will look alike, you have plausible deniability for using that. And the adversary would, in principle, not be able to tell if a specific section of the data was used or not for updating the model. So I have kind of a diagram here explaining how the test works. So you have your original gradient, you add noise, and then you check if within a certain neighborhood you have a threshold T of gradients that are similar. Well, you look into the neighborhood and you see if you have enough gradients. If you have, it passes. You can use that to update the weights of your model. Otherwise, you just reject that. And there are a few interesting theoretical things we can prove about this. We can prove that even though we are talking about batch privacy, it implies privacy also for individual entries of the data set. We can have a game-based definition of privacy here for batches, and we can show that we can derive an individual entry. Basic definition. But there are many differences with DPS, with differential privacy. We don't get to know all the nice properties of differential privacy. The unit of protection, when you take a look at the algorithm, is batch-based. In usual differential privacy, like in the PSCD, it's example-based. We don't have clipping, which increases the utility of our results. And we support any loss function, not just decomposable ones. Decompose means that you have to be able to express the loss function as a sum of individual gradients. We run multiple tests, and for equivalent level, and those are, we'll perform a number of membership inference attacks here. So here is like the attack advantage, the likelihood that you can tell if a sample belongs to the data set or not, the advantage over 1/2 actually. And here is the test accuracy, and you can see that for our method, it clearly outperforms DPSCD, but also outperforms multiple heuristics that have been proposed in the literature before. So we get better utility. We have implemented several different membership inference attacks for multiple data sets with multiple architectures, training from the scratch, but also fine-tuning. I will gladly share those results with you. And I guess I'm out of time. I'm actually over time. So the takeaway here is we have introduced this notion of privacy for training machine learning models that somehow sits in between, what you have, the strong definition that I have with differential privacy and completely, heuristic methods. The computational costs and memory costs are much better than DPSGD, but larger than regular SGD for large batch sizes. And actually, you can prove that if the threshold that we use here is randomized, like you add a random variable according to a certain probability distribution, you can prove that this implies differential privacy if you randomize the test. The epsilons and deltas that you get there are not as good as you would get with DPSGD, which is, I don't think, is the main purpose of this work. Thank you, and sorry for staying over time.
Thank you very much for the very interesting talk. Yeah, question?
Yeah, I have a question on the use case. I mean, why do it inside the model in the training time instead of at the inference time?
Yeah, the problem is, if you're talking about differential privacy,
you're trying to check for privacy.
Yeah.
The same way we do for, let's say, copyright content, right?
Yeah.
Why not do it
There are a few heuristics that work, at inference time. We decided to work on training time here. Yeah, but there are a few heuristics that do that. Yeah.
Is there an advantage to do it?
Oof, honestly, when it comes to differential privacy, if you're talking about a provable guarantee like differential privacy, one problem is adding noise afterwards only works for generalized linear models. Because you have to somehow bound what we call the sensitivity by how much the output of the model changes if you change one entry in the data set, more or less. I'm not being very precise here. But you can only do that we know how to do that for generalized linear models. For something like a neural network or whatever, we don't know, so that's why we clip. We force the change to be that threshold. So for DP, it's a bit difficult. But there are heuristics that do that.
Okay. Thanks again.
Thank you.